Today we're going to talk about integration by parts. If you haven't done so already, go to my website and print out these notes so you can follow along and fill in with me. Integration by parts is an integration technique that you can think of as the product rule in reverse, meaning the product rule from differential calculus. So it's often useful for evaluating indefinite integrals of products, like in this case x times cosine x dx, where this is a product of x and cosine x. So what we want to do is come up with a formula for how to do integrals like this. So we're going to do this once, come up with a formula, and then use the formula. So how might we do this? Well, we can start with the product rule from differential calculus and rewrite it in integral form. Well, what does the product rule say? It says the derivative of uv is u times the derivative of v plus v times the derivative of u. So if we first clear out the denominators by multiplying through by the differential dx, we get this. If we move the v du over to the other side, we get u dv equals duv minus v du. If we then take the antiderivative of each of these three terms, we get this. But look what happens. By the fundamental theorem of calculus, this second thing is the antiderivative of the derivative, really the differential of uv. So that's just uv. If you're not convinced, think of this as having a 1 in front of it. The antiderivative of 1 dx is x. The antiderivative of 1 dy is y. So the antiderivative of 1 duv is uv. In any case, we get this formula, integral u dv equals uv minus integral v du. This is the integration by parts formula, and you need to memorize this, absolutely. I should be able to wake you up in the middle of the night and you should be able to tell me what this is, because you're going to use it all the time. We're going to use this formula to break up a product like the antiderivative of x times cosine x dx. And the trick is to pick what part of this is u and what part of it is dv. So in this case I'm going to pick the u as the x, so this is u, and the dv as the rest of the integrand, cosine x dx. Notice that in the formula we not only need the u and the dv, but we also need other things on the right hand side. We need a v and we need a du. So we need to figure out from the u and the dv what is v and what is du. So if u is x, what is du? Well, if u equals x, then the derivative of u with respect to x is 1. So du dx is 1. Now if du dx is 1, then du is dx. If you need to add the extra step on the side, that if u is x, then du dx is 1, you can do that. But the end result is still that du equals dx. Similarly, on this side, we need to get from dv to v. So this is an antiderivative. If dv is cosine x dx, then what's the antiderivative? Well, the antiderivative of cosine x is sine x. And similarly to this, if you can't see this directly, you can always add the extra step in here of writing something like dv dx equals cosine x. Divide both sides by dx. You've got dv dx equals cosine x, so v equals sine x. Now we use the formula, which I reprinted here, and in this case, what does it say? Well, the left-hand side is what we're starting with, our original question, x cosine x dx, and it equals uv, which is the product of these two, x times sine x, minus the integral of v du, the product of these two, sine x and dx. And let's see what happened. Well, we turned our integral into something else with an integral, but this integral is much easier to do, and that's exactly what we wanted. So now we just have to do the integral that remains. The antiderivative of sine x is negative cosine x, so we get a negative cosine x, which becomes a plus cosine x, and then we throw on a plus c and we are done. So, I wrote on the next page of the notes exactly what we have done. So here's the technique. We viewed the integrand, x cosine x, as a product, choosing u and dv carefully, and making sure that u times dv is the whole integrand. So the key here is to choose the u and the dv carefully. Here are my two tips for this. dv should be an expression, always including the dx, that you can integrate easily without making it worse. So we did that here by choosing dv as cosine x. When you take the antiderivative, it's sine x, which is not any worse than cosine. You choose u to be the rest of the integrand. It's an expression that gets simpler when you differentiate it, and that's what we did here by choosing x. When you differentiate x, you just get 1, so we just got 1 dx. Then you have to find the derivative of u and the antiderivative of dv, and use the formula to transform the original integral into an expression with a hopefully simpler integral. And then we do the simpler integral. Sometimes we have to repeat this process, if necessary, on that integral and finish the problem. So, let's do another example. Antiderivative of x squared natural log x dx. So, this is begging for integration by parts because it's the antiderivative of a product. So we have to set up a u and a dv so that u times dv is the whole integral. Now how should we do this? Well, our u could be x squared and the dv could be ln x dx, or our u could be ln x and our dv could be x squared dx. So how do we know which one to pick? Well, follow these tips. dv should be an expression that you can integrate easily without making it worse. If you choose dv to be ln x dx, for example, can you integrate that easily without making it worse? No. This, in and of itself, the antiderivative of natural log x, is a tricky problem, which we're going to do in a minute, but it's not obvious what that is. So that's a poor choice for dv. A better choice for dv would be x squared dx, the rest of it, forcing u to be natural log x. The other reason this is a good choice is the second tip. U should be something that gets simpler when you differentiate it. And indeed, when you differentiate this, natural log x, you get 1 over x, which is a much simpler expression than natural log. So this is the correct way to start. We then have to go to step 2, find the derivative of u and the antiderivative of dv. So let's do that. du and v. The derivative of u, du dx here, is 1 over x. So if du dx is 1 over x, then du is 1 over x times dx. If the derivative of v is x squared, then what is v? X cubed over 3. Therefore, this integral is uv minus v du, integral v du. uv is x cubed over 3 ln x minus integral v du, x cubed over 3 times 1 over x times dx is x squared over 3 dx. And now we have indeed a simpler integral than our original one to do. So let's finish the problem. This integral is easy enough to do. X cubed over 9 plus c, and we are done. Let's do another example. Antiderivative of x squared sine x dx. It's a product, so we want to use integration by parts. What should our u and dv be? Well, u should be something that gets simpler when you differentiate it. So if u was sine x, that doesn't get any better when you differentiate it. It becomes cosine x, which is about the same complexity. And if you did that, you'd force to have dv be the rest of it, x squared dx. And when you integrate that, it becomes an x cubed, which is worse than x squared. So that's not the right choice. The right choice is for u to be x squared, and for dv to be sine x dx. That way, the derivative of u becomes better. It's a lower degree polynomial with no squares in it. And the antiderivative of sine x, negative cosine x, is not really any worse. So we followed the tips again, outlined in the box on the previous page. So what happens now to our integral? We get uv minus integral v du. So we get x squared times negative cosine x minus the integral of v du, negative 2x cosine x dx. So I'm going to make this a plus, a positive. Now, what about this? This integral is a little bit simpler. It has an x, not an x squared, but it's not obvious how to do this, or what this is right away. We're going to have to use integration by parts again on this integral. So let's do it again. I think we did one that was really similar to this a minute ago, but on this integral, if you choose u is 2x and dv is cosine x dx, we get that the derivative of 2x is 2, and the antiderivative of cosine x is sine x. So, what do we get? Well, we still have the negative x squared cosine x from the original problem, but now we have plus this thing is our new uv 2x sine x minus integral v du. So we just did this times this minus the integral of this times this. 2 sine x dx. Try to make it a point to carry the dx with the dv and the dx with the du. So now what happens? We now have this integral to do, and thankfully this one's easy enough to do just by looking at it. The antiderivative of sine x is negative cosine x. So we have the negative becomes a plus 2 cosine x dx. Oh, sorry, no dx, we just did the integral. So the dx is lost, and I mean plus c. And now we're done. Let's do another example of integration by parts, one that is not as obvious. Look at this strange one. How is this integration by parts? If we think of it as the product rule in reverse, we have to think of this as some sort of product. But it's not obvious. How is this a product? This is natural log x times what? Well, this is a classic example where you have to make it into a product by imagining this as 1 times natural log x. So it's the product of 1 and natural log x. Now, which should be which? Well, if you follow the tips again, dv has to be something you can integrate easily without making it worse. That's 1 dx. And the u is something that gets simpler when you differentiate it. That should be natural log x. Because when you differentiate natural log x, you get 1 over x. So du over dx is 1 over x. So du is 1 over x dx. And if the derivative of v is 1, then v is just x. So this thing then becomes uv minus integral v du. X times 1 over x cancels and you just get 1 dx. But now this is easy. The antiderivative of 1 is just x. And then you throw on a plus c and you're done. I'm going to do one more example of integration by parts with you. This is another classic example of integration by parts. And in this case, something kind of funny happens, and it's worth paying attention to this case. So here's a product, e to the x cosine x dx. So let's happily plod along and see what happens. Let's choose u equals e to the x and dv is cosine x dx. The derivative of u doesn't really get any simpler, unfortunately, but it wouldn't get any simpler if we had chosen this to be cosine x either. So it's good enough. The antiderivative shouldn't be worse, and indeed it's not worse. It's just sine x. So what happens? We get that this thing is equal to uv e to the x sine x minus the integral of v du, which is e to the x sine x dx. Now, unfortunately, this thing is not simpler than the original, so it looks like we've failed. But keep the faith and do it again. Let's try it. Maybe it'll work on this one. So to do this integral that we're left with, we have to do integration by parts again. U equals, let's do it again, e to the x, dv is sine x dx. Again, if u is e to the x, the derivative is e to the x dx, and the antiderivative of sine x is negative cosine x. So what happens? Minus, this thing becomes uv negative e to the x cosine x minus integral v du, e to the x times negative cosine x. So I'll make that a plus because we have two negative signs. And we get this. Let's just simplify this a little bit. E to the x sine x plus e to the x cosine x plus integral e to the x cosine, minus, that's a minus. Minus the positive is a minus. E to the x cosine x dx. So, well, now look at this. It looks like we've really failed now because we're back to the beginning. We now have to do this integral, which is the same as what we started with. So it would be tempting at this point to give up and say this technique doesn't work on this integral. But there's a trick. If we call this integral, go back up to the top and call it A, standing for answer. Our answer that we want is whatever this is. Then what is this? This is e to the x sine x plus e to the x cosine x minus A, because this whole thing is our original object. So now we have this equation, A equals some expression with A, and we can solve it for A and get our answer. So I'll move the A down here. A equals e to the x sine x plus e to the x cosine x minus A. If we add A to both sides, we get 2A equals e to the x sine x plus e to the x cosine x. Divide both sides by 2. We have our answer. We are done, except for a plus c. And that's that. So if you ever see something that looks like this, e to the x cosine x, sometimes with little other constants or coefficients added in, or multiplied, you can do this trick where you get this sort of recursion where you come back to the beginning after doing integration by parts twice and then solve the equation to get your answer. Now, the next thing you should do after you understand the examples here is you should try these 3 on your own, and then you're ready to do whatever homework has been assigned in your class. One more thing to say is that some people like this time-saving tip for problems involving repeated integration by parts, where you have to do it more than once in the same problem. And it's something called the tic-tac-toe method usually, and you can Google that if you're interested, but I won't be talking about it.